Electrical circuits are fundamental to modern technology. Understanding the relationship between voltage, current, and resistance is essential for anyone working with electronics or electrical systems. Ohm's law is the cornerstone of this understanding. It describes the relationship between voltage, current, and resistance in an electrical circuit. Voltage, measured in volts, is the electrical potential difference that drives the flow of charge. It is the push that causes electrons to move through a circuit. Current, measured in amps, is the rate of flow of electric charge. It represents the number of electrons passing a point in a circuit per unit of time. Resistance, measured in ohms, is the opposition to the flow of current. It hinders the movement of electrons through a circuit. Ohm's law states that voltage is equal to current multiplied by resistance. Mathematically, this is expressed as volts equals amps times ohms, or volts equals I times R. This equation can be rearranged to solve for current or resistance as well. For example, current equals volts divided by resistance, or I equals volts divided by R, and resistance equals volts divided by current, or R equals volts divided by I. Let's consider a simple circuit with a 12 volts battery and a 6 ohms resistor. Using Ohm's law, we can calculate the current flowing through the circuit. Current equals volts divided by resistance, so I equals 12 volts divided by 6 ohms, which equals 2 amps. Therefore, the current flowing through the circuit is 2 amps. Now let's consider a circuit with a 5 volts power supply and a current of 0.5 amps. We can calculate the resistance using Ohm's law. Resistance equals volts divided by current, so R equals 5 volts divided by 0.5 amps, which equals 10 ohms. Therefore, the resistance in the circuit is 10 ohms. These calculations demonstrate the application of Ohm's law in determining voltage, current, and resistance in simple circuits. Electrical circuits can be configured in different ways, with the two most common configurations being series circuits and parallel circuits. In a series circuit, components are connected end-to-end, forming a single path for current to flow. The current is the same through all components in a series circuit. However, the voltage is divided among the components. The total resistance in a series circuit is the sum of the individual resistances. For example, if we have 3 resistors in series with resistances of 2 ohms, 4 ohms, and 6 ohms, the total resistance would be 2 ohms plus 4 ohms plus 6 ohms, which equals 12 ohms. The voltage drop across each resistor can be calculated using Ohm's law. If the total voltage applied to the series circuit is 24 volts, the current flowing through the circuit would be 24 volts divided by 12 ohms, which equals 2 amps. The voltage drop across the 2 ohms resistor would be 2 amps times 2 ohms, which equals 4 volts. The voltage drop across the 4 ohms resistor would be 2 amps times 4 ohms, which equals 8 volts. And the voltage drop across the 6 ohms resistor would be 2 amps times 6 ohms, which equals 12 volts. Notice that the sum of the voltage drops across the resistors equals the total voltage applied to the circuit, which is 4 volts plus 8 volts plus 12 volts equals 24 volts. In a parallel circuit, components are connected side by side, providing multiple paths for current to flow. The voltage is the same across all components in a parallel circuit. However, the current is divided among the components. The total resistance in a parallel circuit is calculated differently than in a series circuit. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. For example, if we have 3 resistors in parallel with resistances of 2 ohms, 4 ohms, and 6 ohms, the reciprocal of the total resistance would be 1 divided by 2 ohms plus 1 divided by 4 ohms plus 1 divided by 6 ohms. This simplifies to 6 divided by 12 plus 3 divided by 12 plus 2 divided by 12, which equals 11 divided by 12. Therefore, the total resistance would be 12 divided by 11 ohms, which is approximately 1.9 ohms. The current through each resistor can be calculated using Ohm's law. If the voltage applied to the parallel circuit is 12 volts, the current through the 2 ohms resistor would be 12 volts divided by 2 ohms, which equals 6 amps. The current through the 4 ohms resistor would be 12 volts divided by 4 ohms, which equals 3 amps. And the current through the 6 ohms resistor would be 12 volts divided by 6 ohms, which equals 2 amps. Notice that the sum of the currents through the resistors equals the total current flowing into the parallel circuit, which is 6 amps plus 3 amps plus 2 amps equals 11 amps. Understanding the differences between series and parallel circuits is crucial for designing and analyzing electrical systems. Series circuits provide a single path for current, while parallel circuits provide multiple paths. The total resistance and current distribution differ significantly between the two types of circuits. In practical applications, electrical circuits often involve combinations of series and parallel connections. These circuits can be analyzed by breaking them down into simpler series and parallel equivalents. For example, a circuit might have 2 resistors in series connected in parallel with another resistor. To analyze the circuit, one could first calculate the equivalent resistance of the 2 resistors in series, and then calculate the equivalent resistance of the combination in parallel with the third resistor. This approach allows one to simplify complex circuits and determine the overall voltage, current, and resistance characteristics. In addition to Ohm's law and series and parallel circuit analysis, it is also important to consider power in electrical circuits. Power, measured in watts, is the rate at which electrical energy is transferred. Power is equal to voltage multiplied by current, or watts equals volts times amps. Using Ohm's law, power can also be expressed as watts equals I squared times R, or watts equals volts squared divided by R. Understanding power calculations is essential for determining the energy consumption of electrical devices and for ensuring that circuits are properly designed to handle the required power levels. For example, if a device operates at 120 volts and draws 2 amps of current, the power consumption would be 120 volts times 2 amps, which equals 240 watts. This information can be used to select appropriate wiring and circuit breakers to protect the circuit from overload. Furthermore, it is crucial to understand the concept of short circuits and open circuits. A short circuit occurs when there is a low resistance path between 2 points in a circuit, typically bypassing a component. This can result in a very high current flow, which can damage components and create a fire hazard. A short circuit can be caused by damaged insulation, loose connections, or accidental contact between conductors. An open circuit occurs when there is a break in the circuit, preventing current from flowing. This can be caused by a broken wire, a blown fuse, or a faulty switch. An open circuit will result in no current flow and the circuit will not function. Troubleshooting electrical circuits often involves identifying and resolving short circuits in open circuits. This can be done using a multimeter to measure voltage, current, and resistance at various points in the circuit. By carefully analyzing the measurements, one can often pinpoint the location of the fault. Electrical safety is paramount when working with electrical circuits. Always disconnect power before working on any circuit. Use insulated tools and wear appropriate personal protective equipment such as safety glasses and gloves. Never work on electrical circuits in wet or damp conditions. Be aware of the potential hazards of electricity and take precautions to avoid electrical shock and burns. It's also important to understand the color codes for resistors. Resistors are often marked with colored bands that indicate their resistance value and tolerance. Each color represents a different number, and the position of the bands indicates the significance of the numbers. For example, a resistor with bands of brown, black, red, and gold would have a resistance of 1000 ohms with a 5% tolerance. Online calculators and charts are readily available to help decode resistor color codes. Capacitors are another important component in electrical circuits. Capacitors store electrical energy in an electric field. They are used in a variety of applications such as filtering, smoothing, and energy storage. The capacitance of a capacitor is measured in farads. Capacitors can be connected in series or parallel, and the total capacitance is calculated differently for each configuration. Inductors are also commonly used in electrical circuits. Inductors store electrical energy in a magnetic field. They are used in applications such as filtering, energy storage, and electromagnetic interference suppression. The inductance of an inductor is measured in henries. Inductors can also be connected in series or parallel, and the total inductance is calculated differently for each configuration. Diodes are semiconductor devices that allow current to flow in only one direction. They are used in applications such as rectification, signal processing, and voltage regulation. Transistors are semiconductor devices that can be used as switches or amplifiers. They are fundamental components in modern electronic circuits. There are two main types of transistors: bipolar junction transistors and field effect transistors. Integrated circuits, or chips, are complex circuits that contain millions or even billions of transistors and other components on a single piece of silicon. They are the building blocks of modern electronics and are used in everything from computers and smartphones to automobiles and appliances. Understanding the basic principles of electrical circuits, including Ohm's law, series and parallel circuits, power calculations, and the characteristics of various components, is essential for anyone working with electronics or electrical systems. By applying these principles and following safe practices, one can design, analyze, and troubleshoot electrical circuits effectively. Furthermore, it is essential to stay updated with the latest advancements in electrical and electronic technologies. This field is constantly evolving, and new components, techniques, and standards are being developed all the time. Continued learning and professional development are crucial for staying competitive and effective in this dynamic field. The NEC, or National Electrical Code, provides standards for safe electrical installations. These standards cover topics such as wiring methods, overcurrent protection, grounding, and equipment installation. Adhering to the NEC is essential for ensuring the safety of electrical systems and preventing electrical hazards. Electrical drawings and schematics are used to represent electrical circuits and systems. These drawings use symbols to represent components and lines to represent connections. Understanding electrical drawings is essential for designing, installing, and maintaining electrical systems. There are different types of electrical drawings, including single-line diagrams, schematic diagrams, and wiring diagrams. Each type of drawing provides different levels of detail and is used for different purposes. Multimeters are essential tools for working with electrical circuits. They can be used to measure voltage, current, resistance, and continuity. Understanding how to use a multimeter is crucial for troubleshooting electrical problems and verifying circuit performance. Oscilloscopes are used to visualize electrical signals. They can display voltage as a function of time, allowing one to analyze the waveform of a signal. Oscilloscopes are useful for troubleshooting complex circuits and identifying signal distortions. Signal generators are used to create electrical signals. They can generate a variety of waveforms such as sine waves, square waves, and pulse waves. Signal generators are used for testing and characterizing electrical circuits and systems. Power supplies are used to provide a stable and regulated source of electrical power. They convert alternating current volts from the power grid into direct current volts suitable for powering electronic devices. There are different types of power supplies, including linear power supplies and switching power supplies. Finally, understanding the principles of grounding and bonding is essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, helping to prevent electrical shock and equipment damage. Bonding connects metallic parts of a system together to equalize their potential, reducing the risk of electrical shock. This comprehensive overview provides a foundation for understanding electrical circuits and related concepts. Further study and practical experience are essential for developing expertise in this field.